Virtual reality techniques can modify how physical body movements are mapped to the virtual body. For example, users can have longer fingers when playing the piano or reach way further in VR than their physical arm could reach. They can also have supernatural body structures like an additional limb or tail, or control the body differently, such as using fingers to move the whole arm. When a VR interaction technique introduces such a movement mapping, the user must learn it. In this work, we are interested in understanding and quantifying how users learn such new movement mappings. Currently, task completion time and completion errors are primary metrics to evaluate user performance in human-computer interaction research. However, they provide little insight into the learning process because they just approximate how good the users are, without revealing the underlying reasons for changes in user performance. So, they fail to inform how the techniques could be improved. We consulted the motor learning literature, primarily studied in psychology and physiology, to quantify the learning process more precisely. We then designed 4 new metrics explicitly for VR and HCI interactions. We devised 4 new metrics. Refinement time proportion and refinement space assess user prediction error by assuming the initial movement impulse, or so-called ballistic phase, represents the initial user prediction without correction movements. Normalized path error represents the percentage of the extra movement compared to the ideal shortest path. Normalized jerk error measures the extra jerk applied in the current movement compared to the ideal movement governed by the minimum jerk assumption. We designed a user study to evaluate the proposed metrics in 3 common VR interaction tasks employing 1 new movement mapping type in each. The first task requires users to move a 3D cube to a target position on the table, with or without a linear translational gain. The second task requires users to rotate a 3D bunny to a target orientation, with or without a non-linear rotational gain. The third task requires users to select a target with direct touch or finger-to-arm mapping. The study shows that the metrics demonstrate known characteristics of motor learning, typically with faster initial learning followed by more gradual improvements over time. More importantly, the metrics capture learning behaviors when task completion time does not. We discuss how the metrics can provide insights into how users adapt to new mappings and how they can help analyze VR techniques. Please read our paper to find out more. See you there.